for a fresh new view. Turn your heads, it's time you knew. No time for FUD or the hype. It's too untrue. Open up your Twitter, you know you want to. Drop tweets on what we gonna do. He won't stop till he rocks you.
Chad's World, because life is orthogonal. Chad's World, you gotta rock the original. Chad's World.
I've saved the most mind-blowing customer example and story for last.
You got more?
We always have more, man.
Does it scale out?
This is a scale-out story like the likes of which I've never seen before, right? So, Gary, why don't you come on up, man?
Come on up, Gary.
I think we got to get Gary a Red Bull, or at least a beer.
You got it. Sure we have.
So, Gary's story is the coolest one, and this is a real struggle to illustrate. So we're going to try something a little bit funky here because...
Thank you.
Well, why don't we do this? Gary, tell everybody here who you are, who you work for, first of all.
I'm Gary Grider. I'm the High-Performance Computing Director at Los Alamos National Lab. We manage the nuclear stockpile for the U.S. Government, and we do that by not testing anymore because people didn't like testing too much. And so we simulate weapons instead of blowing them up, and that takes really large computers to do.
So hey, thank you for, we all are indebted to all the work you guys do, protecting us and without nuking things, right? I think most of us don't live in your world. So I'm going to try to make this bit by bit clear to everybody here, the kind of things we're talking about. So an example of a simulation would be something like the asteroid impact that killed the dinosaurs. So this is actually the real simulation of an asteroid crashing into the crust of the Earth and the magma exploding up about 12 kilometers up into the upper atmosphere that destroyed all of the dinosaurs.
Wow.
Right? By the way, that video little segment took about like 15 seconds.
Yep.
What's behind the scenes of that sort of simulation?
That's probably 40 or 50 million computing core hours.
40 to 50 million computing core hours. Okay, whoa. Right? Okay, whoa. So
that's a long time.
We're talking big right now. Obviously, it would be better if we didn't actually get hit by the asteroid, right?
That would be good.
Yeah, I like that.
So another example of things that you would model in these giant simulations would be something like...
Maybe destroying it before it gets there.
Exactly. So let's see what it looks like if you nuke an asteroid.
Nuke an asteroid.
That is a model of a nuclear weapon detonating on an asteroid, to basically figure out, hey, how would this thing explode and get destroyed, hopefully before it destroyed all humanity. Again, woo, that's good.
I like that.
Right? So as an example, again, I'm gonna bit by bit. This is such a cool story. You got to have your mind blown one step at a time.
We had to have face melting.
So face melting and mind blowing all together all at once. So like today, the kind of supercomputers that you guys are talking about, how many CPU cores would you consider quote unquote normal?
500,000.
500,000 CPU cores. Now that is scaling out, right? So the thing that's fascinating to me about this is, as I was learning from you and kind of figuring this out, it's different than like a Hadoop cluster or those sorts of things. Literally, they have a distributed memory state. Like the whole memory state of this thing has to be stored, because when you have that many cores, they fail all the time, right?
All the time.
Right? So as they fail, the state of the simulation needs to be reloaded, right? So how often do you guys have to basically back up the entire memory state of the system, roughly?
Today, 4 hours.
So 4 hours, every 4 hours, you've got to take a dump of the system just in case a host gets hosed somewhere. And then maybe you'd use something like Razor and Puppet to automate the build of that new server and bring it back up. But then you have to reload the memory state, right? So now, today, the storage subsystems that are needed to do that have roughly about how many spindles?
30,000.
We scale out.
Yeah. So you're a little too subdued for such a cool job, man. So now I want to put this again in a little bit of broader perspective. That's today, right? So if you wanted to scale to, exascale, an exaflop supercomputer, right? How many cores roughly would you need?
About 1 billion.
About 1 billion. This is basically a small city, right, that is a supercomputer, right? Right?
We scale out.
That's a big scale out example. Now, this is where it just gets whack. Like if you think that it wasn't whack before, this is where it gets whack, right? So the problem is that as you have more and more and more nodes, right, the likelihood of any one of them failing, right, stays the same, but the likelihood of any node in the entire cluster goes way up.
Yep.
Which means that the memory state dump needs to happen a lot faster.
Yes.
Right? And we have 1,000 times more information, so we have to do 1,000 times more information dumped into the system, and we have to do it 10 times faster, roughly, right? So if you were to build this, it would cost a lot. If you used like an all-flash config, how much did you guys estimate?
The cost?
The cost.
$500 million.
About $500 million for the storage subsystem. I mean, for some EMC sales rep somewhere, it's like cha-ching, cha-ching, right?
I'm going to work for Billy.
Now clearly, that's not going to work, right? As awesome as that would be, right? Right. So we needed to come up with a better way, right? Mm-hmm. So the first innovation that you guys at Los Alamos National Lab came up with is something called
Parallel log structured file system.
Okay, so I'm going to do the Chad decoder on this, having like listened for a long time. PLFS, Parallel Log Structured File System, is like a meta file system, right? It's a file system that kind of lives across other file systems. So you could have it on top of, and this is the example that you guys are actually using, VNXs using Lustre, but it could be other file systems too, right? So if we wanted to do this memory state dump, again, I want to put this in perspective. How much memory would we need to dump and how fast for this exascale supercomputer?
50 petabytes of memory in 5 minutes.
Petabytes? Petabytes?
So you guys saw that we just announced Isilon is like the fastest thing on the planet, right? And it can do like hundreds of gigabytes per second. He's talking about like 100 terabytes per second. Like cuckoo. Right? And you need to have enough scratch space to store a couple of these memory state dumps. So like how big, roughly?
Approaching an exabyte.
About an exabyte of storage, give or take. So clearly you need to have something that could stitch together all sorts of multiple different file systems together, but it would also have to deliver better performance, right? So what PLFS does is it parallelizes the IOs into the file systems, which could be many, 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 many file systems, right? And it also makes the IOs into them sequential. So again, to make this clear, let's show a little example of the old way, right? And we'll bring it up on the screen. This is the old-fashioned, oldie-timey file system. In this case, it's actually just Lustre, which isn't oldie-timey, but it's just a single Lustre kind of system running on one thing. And you can see that the disk utilization is just not that high across all of the disks in the system. It's kind of like bump, bump, bump. PLFS, aka what I call the new coolness, looks like this, right? So much, much higher utilization of any underlying file system. Again, the example that we're doing today is high-performance computing using, Lustre on top of VNX. We could use the Terascale, partnership that we've got around high-performance computing. Could also be Isilon against the back end, because you have to stitch together many, many, many things. So that's cool. Was that enough?
Nope.
Right. Not even close, right? So then, basically, the EMC team and Los Alamos National Lab teamed up, and they built something that you guys call
ABBA.
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 No, it's not a 1970s Swedish supergroup.
I thought you were the dancing queen, Chad.
Dancing Queen. If you Google Cloud Freak, you'll see I've got some moves. I got
the moves like Jagger, though.
You have the moves like Jagger. So basically, what we've developed here together, right, is this thing called an active burst buffer appliance. Again, I'm going to bring up a diagram so you can kind of get this idea. So imagine racks and racks of compute nodes, right, that are actually using, they're using the computing to run the actual simulation, right? Now each one of them has, basically the simulation code on it, but it also is running PLFS. So they're participating in like one uber mega, meta file system, right? Now underneath there's an underlying file system, and what we put in the middle are these ABBA nodes. And the ABBA nodes are basically, again, servers with solid state in there, and it's using Flash as like a staging cache. So what that means is instead of the drain going all the way down to the underlying file system, what happens is the compute nodes say, hey look, we're going to open the file that is in essence this huge petabyte, scale thing, this file that's going to be a giant checkpoint of the entire system. And then what happens is it creates pointers towards the ABBA nodes. The burst of this huge, right, 100 terabyte second just stream, terabyte per second stream, comes down and it hits these nodes that absorb it, right, using Flash as a staging area, right? So we're using a little bit of Flash to go a long way, right? Does that make sense to everybody here? You've heard it. Flash first works. A little bit of Flash can make a huge, huge difference.
Love
right? It. Now, ultimately, what then happens is that the ABBA nodes drain the data to the underlying file system, but that can happen in a decoupled way, right? So we can handle the huge burst and then dump it down to very, very large capacity underlying storage that can store the giant, giant petabyte or exabyte scale kind of needs that you guys have got, right? But then what happened through this was this innovation realization. You notice how it says, GPGU? That's like a general purpose graphics processing unit. It's a thing that's used to run visualization. Like humans are not really good at reading just pure math. Right?
That's right.
So, well, you guys really dug those videos, right? People need to see things to really understand them, right? So what occurs is instead of running the visualization right at the end, you can
run it while it's simulating.
Exactly, right? So if you think about what that means, right, is it means that you can do a lot of work in parallel. Now again, remember, I'll show you the data that we've done out of our early testing around this, but remember, I've drawn one little example. If you imagine racks and racks and racks and racks going to the point where you have 1 billion CPU cores, that's what he does for a living.
He has the cool data center.
That's pretty cool. So this is a compare. This is a compare of like without ABBA and with ABBA. Without ABBA, you don't have that great singing and dancing tunes that we all love. With ABBA, you all just want to groove and be dancing queens, right? No, okay. In all seriousness, without ABBA, this is what it looks like. Basically, you've got the CPU time, which is that orange bar. Underneath, you've got the green bar, which is basically the stream, the dump of the checkpoint state. And at the end, those little blue bars are the visualization efforts, right? With ABBA, and this is again a smaller scale example, but literally it's a model that scales linearly. You can see there's a huge fast drain, like the burst phase is super, super fast, and then the drain occurs kind of as a background process, and you can see that we can do the visualization at the same time that we're doing the compute. Does that make sense? Is that cool?
Is that cool or what?
I was like, this is one of the cool, like, again, you're a modest man. I thought this is one of the coolest stories I've ever seen, right? I can't even imagine that kind of scale, right? And again, it's kind of cool, as you guys have seen, EMC, we ain't just a storage company. We are the best storage company. Yes, right?
In scale.
Yeah? Woo! Can we stand to improve? Absolutely. But we are the best, right? How awesome was that video during, the keynotes? Literally, my face was like melted. I was in the free.
I was getting dizzy.
But obviously, there's so much more underneath the covers of what we do. Things like Project Razor, right? This crazy cool innovation that we're doing together around these massive scale things that are so alien to all of us, but are the life of Gary day in and day out, right? So I just thought it was a really cool example, and for what it's worth, I wanted to say thank you.
Thank you.
For meaning that we don't have to actually deploy nukes, right, to do this sort of testing.
Amen.
Right?
Amen.
Thank you. And I wanted to kind of ask a quick question. So with that, so if you can do all that stuff today using the sort of, you know, millions and millions of cores, what the heck would you need a billion CPU cores for?
If I told you, I'd have to have you killed.
We don't want that. Our insurance isn't high enough.
Gary, thank you so much. Very much appreciated.
Thank you.
I'm looking forward to enjoying the beer with you.
How cool is that? Chad, come on. You scale out.
We scale out.
He scales way out.
Yeah, we do scale out at EMC. He scales way out, right?